Columbia researchers engineered first technique to exploit the tunable symmetry of 2D materials for nonlinear optical applications, including laser, optical spectroscopy, imaging and metrology systems, as well as next-generation optical quantum information processing and computing. Nonlinear optics, a study of how light interacts with matter, is critical to many photonic applications, from the green laser pointers we are all familiar with to intense broadband white light sources for quantum photonics that enable optical quantum computing, super-resolution imaging, optical sensing and ranging, and more. Through nonlinear optics, researchers are discovering new ways to use light, from getting a closer look at ultra-fast processes in physics, biology, and chemistry, to enhancing communication and navigation, solar energy harvesting, medical testing, and cybersecurity. Columbia engineering researchers report that they developed a new, efficient way to modulate and enhance an important type of nonlinear optical process, that is, optical second harmonic generation, where two input photons are combined in the material to produce one photon with twice the energy, from hexagonal boron nitride through micromechanical rotation and multilayer stacking. The study was published in the journal Science Advances. The researchers say their work is the first to exploit the dynamically tunable symmetry of 2D materials for nonlinear optical applications. A hot topic in the field of 2D materials has been exploring how twisting or rotating one layer relative to another can change the electronic properties of the layered system, something that can't be done in 3D crystals because the atoms are bound so tightly together in a 3D network. Solving this challenge has led to a new research area termed twistronics. In this new study, the team used concepts from twistronics to show that they also apply to optical properties. The researchers are calling this new research area twist optics. Their twist optics approach demonstrates that we can now achieve giant nonlinear optical responses in very small volumes, just a few atomic layer thicknesses, enabling, for example, entangled photon generation with a much more compact chip-compatible footprint. Moreover, the response is fully tunable on demand. Most of today's conventional nonlinear optical crystals are made of covalently bonded materials such as lithium niobate and barium borate. But because they have rigid crystal structures, it is difficult to engineer and control their nonlinear optical properties. For most applications, though, some degree of control over a material's nonlinear optical properties is essential. The group found that van der Waals multilayer crystals provide an alternative solution for engineering optical nonlinearity. Thanks to the extremely weak interlayer force, the researchers could easily manipulate relative crystal orientation between neighboring layers by micromechanical rotation. With the ability to control symmetry at the atomic layer limit, they demonstrated precise tuning and giant enhancement of optical second harmonic generation with micro-rotator devices and superlattice structures respectively. For the superlattices, the team first used layer rotation to create twisted interfaces between layers that yield an extremely strong non-linear optical response, and then stacked several of these twisted interfaces on top of one another. The group's findings have several potential applications. Tunable second harmonic generation from micro-rotators could lead to novel on-chip transducers that couple micromechanical motion to sensitive optical signals by turning mechanical motion into light. This is critical for many sensors and devices such as atomic force microscopes. Stacking multiple boron nitride thin films on top of each other with controlled twist angle demonstrated greatly enhanced nonlinear response. This could offer a new way to manufacture efficient nonlinear optical crystals with atomic precision. These could be used in a broad range of laser, optical spectroscopy, imaging, and metrology systems. And perhaps most significantly, they could provide a compact means for generating entangled photons and single photons for next generation optical quantum information processing and computing.